Hello, ladies and gentlemen. Welcome at webinar of company NenoVision. My name is Jiří Očatík and I will guide you through the webinar today. We want to demonstrate capabilities of our atomic force microscope product, which is named LiteScope. This webinar is intended for users, distributors, sellers, and professional public indeed. We just opened event Q&A sessions, which is moderated, and you are invited to use it. I'm very happy that I can work today with my colleagues Josef Horák and Veronica Hargrove, who are our experts in field of AFM applications. Please ask questions at any moment. Sessions are not live, they are pre-recorded. Josef and Veronica are free to write answers at very same moment when you can see them on the screen. So yes, they will be utilized twice, but for them indeed without additional bonus. Your voice feedback is disabled. We cannot hear you. Writing questions is the only way of your communication to us. This is not that we wouldn't like to communicate with you, but we must ensure a smooth broadcasting for many people and follow GDPR rules when recording session. I believe everyone understands it. There is a relatively long delay between our broadcasting and your hearing. Don't expect our fast reaction, so there are really tens of seconds. I hope that the hearing is not the other way around and you can hear me and my colleagues. Now about the program. The webinar content has been inspired by our standard roadshow. We always start roadshow by installation of LiteScope into SEM. However, it takes more than half an hour. In the meantime, we open an introductory lecture about LiteScope and AFM. Then we measure and demonstrate to our audience. Today we will follow it the same way. Josef first will explain all secrets of AFM technology, our solution, various probes and measuring modes. Then Veronica will demonstrate how easily she can install the LiteScope into the scanning electron microscope. Later, she will show you how to operate it and how to get results quickly and reliably. Now I will give floor to our senior application specialist, Josef Horák, who will tell you about LiteScope. Enjoy.
Welcome, my name is Josef Horák. I am the Senior Application Specialist at NenoVision, and I would like to introduce NenoVision's unique atomic force microscope, called LiteScope, which is designed to be easily integrated into a variety of scanning electron microscopes. I will explain all the benefits coming from the atomic force microscope and scanning electron microscope connection with focus on correlative imaging. NenoVision was founded in 2015 as a spin-off of Brno University of Technology and the Central European Institute of Technology. Brno is a city of universities, technology and science with rich history of microscope development. That is why both Thermo Fisher and T-scan electron microscope divisions are located here. And it is estimated that approximately 30% of all scanning electron microscopes in the world come from Brno. Atomic force microscopes and scanning electron microscopes are two of the most, and in fact complementary techniques for sample analysis in the nanoscale. Nevertheless, since the principle with which they observe and interact with the sample surface is completely different, they provide very different set of information. AFM monitors interaction between a physical probe and the sample surface, while a scanning electron microscope observes and analyzes the sample surface using a focused beam of electrons. And based on this, AFM represents a tool of choice for topography and roughness measurement with sub-nanometer resolution. AFM also enables analysis of mechanical, electrical, and magnetic properties. On the other hand, SEM electron beam interaction with the sample surface produces various signals. So beside fast 2D imaging in wide range of resolutions, SEMs can provide information of sample composition as well. Further possibilities of SEMs, such as surface modification or nanomanipulation, will depend on their additional accessories. So why to actually combine AFM and SEM together? So the motivation behind LiteScope design is as follows. Well, first of all, the AFM in SEM systems allows for efficient yet complex in-situ sample characterization that combines capabilities of both techniques. Second, it brings completely new possibilities for advanced correlative imaging, which allows analyzing samples in a way that was difficult or even impossible by separate SEM and AFM systems. So let's have a quick look at an example of tungsten diselenide flake placed over silicon pillars. So in the left, there's an AFM image showing three-dimensional topography. On the right side, there's a SEM image that provides great material contrast, and in the middle, you can see the correlated image that clearly provides more information about the sample that would have otherwise been possible using each imaging modality separately. And that leads us to the key benefits of the AFM in SEM approach. So first of all, it is extremely useful to utilize SEM for precise AFM navigation. Then it provides clear difference between material and topography contrast. Next point is 3D profiling of nanostructures in in-situ conditions, which is crucial for surface modification using, for instance, focused ion beam or gas injection system, and also for sensitive samples. And lastly, it allows for in-time AFM and SEM data correlation by a technique we call CPAM. And CPAM stands for correlative probe and electron microscopy, and it represents next step in correlative imaging. So let's have a look on how it actually works. So on the sample, the electron beam points close to the AFM tip with a constant offset. And during scanning, the AFM tip and electron beam remain static, and sample is being scanned only by the LiteScope piezo scanner, which enables simultaneous detection and acquisition of AFM and SEM signals at the same time, in the same place, and under the same conditions. So this technology is unique to LiteScope and was developed for seamless data correlation. So the captured AFM and SEM images are subsequently correlated into one image, which we call three-dimensional CPAM view. And CPAM view can contain multiple channels as shown on the sample of tungsten chromium. So for this particular application, the AFM topography was correlated with the data from secondary electrons and backscattered electron detectors. And CPAM can be also visualized in this short capture of an actual measurement. So in SEM, you can see the AFM tip scanning over a graphene flake on a copper substrate, and 5 different channels are being recorded at the same time in the NanoView software. So 3 channels, topography, energy dissipation, and an error, come from the AFM, and 2 channels, SE and BSE, from the SEM. And of course, combination of appropriate channels can be chosen for your particular application. In the next part, I will quickly present more details about LiteScope. Our company has 2 main product categories, the first of which is the LiteScope package, and the second are LiteScope accessories. So the LiteScope package contains LiteScope scan head, the control unit called NanoBox, our software NanoView, and then adapters, flanges, and feed-throughs for specific SEMs. In the category of LiteScope accessories, you can find, for example, custom sample holders or variety of tools that are usually developed for specific applications. We also offer AFM probe and sample exchange through a load log, so you don't have to break the vacuum in the SEM chamber, then a special storage case called Nanocase, which enables you to use LiteScope as a standalone AFM. Lastly, a nano indenter module can be added to the LiteScope in order to combine 3 complementary techniques, AFM and SEM, with nano indentation for advanced characterization of materials' mechanical properties. Let's have a look at some of the key features and standard configuration of LiteScope. As said already, LiteScope is designed for vacuum environment and integration into SEM. The integration is very fast, it usually takes under 10 minutes. Nevertheless, LiteScope can be used as a standalone AFM. It is important to mention that LiteScope is highly customizable. We offer two different scanner configurations. The standard configuration offers big scan range, 100 by 100 by 100 microns, with resolutions up to 0.2 nanometers. The custom configuration has a reduced scan range to 38 by 38 by 38 microns, however, with increased resolution up to 70 picometers. Then we offer two different macro approach configurations and also LiteScope version for field-free and immersion SEMs. And since LiteScope can be tilted, it is compatible with standard SEM accessories such as focused ion beam, gas injection system, and so on. LiteScope supports a wide range of measurement modes. So starting with mechanical properties, we offer topography, then measurement of local elastic properties by energy dissipation in tapping mode, or by force modulation microscopy in contact mode. You can also measure the local sample hardness by force distance curves, and then you can use the AFM probe for nano indentation and nano manipulation. So when it comes to the electrical properties, you can use the standard conductive AFM in order to do conductivity map, or its extended version, conductive CPAM, which will allow you to do conductivity map, however, including insulated areas. Then you can measure local surface potential by Kelvin probe force microscopy, and then you can establish the local electrical properties by electrical spectroscopy, and you can also do scanning tunneling microscopy. And if your sample contains piezoelectric domains, you can image them by piezo response force microscopy. So the sensing probes are crucial components of every AFM measurement, and when it comes to the AFM probes, NenoVision has chosen a different way. So instead of producing our own proprietary probes, we designed LiteScope to be fully compatible with commercially available self-sensing probes. So it contains universal acceptor for appropriate probe holders. Also, its design enables easy and fast probe replacement with pair of tweezers. Our software contains preset settings for every supported probe as well. And as for now, LiteScope supports 3 types of tuning fork-based probes, 2 types of piezo-resistive silicon probes, and also a conductive wire. And if you would like to use self-sensing probe that is not on the list, we will do our best to develop a probe holder suitable for your probe. And at the end of this part, I would like to demonstrate performance of silicon carbide sample, which is an AFM calibration standard. As you can see, we were able to easily measure individual terraces, and we would demonstrate high performance of LiteScope on the height noise level at 50 picometers and calculated surface roughness of 180 picometers. Now let's talk about the main application areas for combined AFM and SEM instruments. We have categorized a broad range of different applications in material science, such as 1D and 2D materials, steel and metal alloys, and various nanostructures, and then semiconductors and life science. So in the displayed applications, the in-situ CPAM correlative imaging was the primary goal, however, usually put together with other properties of the sample, such as the characterization of mechanical or electrical properties. So one of the nice examples of the AFM-in-SEM combination benefits is the analysis of Duplex steel, where you can identify individual steel grains, precisely measure their topography, and nicely distinguish between 2 different steel faces. And the result is a fantastic correlation of topography with SE and BSE signals from SEM showing strong contrast of individual metal faces. So correlative CPAM imaging provides ideal tool for multiple data analysis. And also this application is an ideal candidate for the nano-indenter module, which enables nano-indentation with a single grade precision. Another example nicely shows how the combination of AFM with SEM equipped with focused ion beam can be utilized to optimize the focused ion beam milling process. So for this purpose, cadmium telluride was sputtered using increasing doses of ions as depicted in the SEM image. And each of these 10 frames were immediately analyzed by AFM and SEM in in-situ conditions, and the data were correlated and used to optimize the ion dose intensity. And because cadmium telluride represents a heterogeneous material, the AFM topography can be used to achieve desired surface profile. And of course, since the complete analysis is done in in-situ conditions, this can be used even for sensitive samples such as cadmium telluride. So here I'm going to show you some of the most common measurement modes for characterization of material electrical and mechanical properties. So let's start with the electrical properties, and namely with conductive AFM and conductive CPAM. And for that I'm going to use sample where silicon is covered by gold, and the gold creates areas that are conductive, non-conductive, and some of them are conductive but insulated. So if you will do the standard conductive AFM, we will be able to image only the areas that are conductive. However, we can take advantage of the close proximity of the conductive AFM tip to the SEM E-beam, and we can use this E-beam as external source of electrons. And that will enable us to image also the areas that were conductive but insulated. So let's move on to the Kelvin probe force microscopy that we'll use to map the surface potential on a sample that contains some parts of alumina, silicon, and gold. So in the lower part of the sample, you can see the topography, and in the upper part, you can see the potential imaging. And next example is electrical spectroscopy. So here we had a sample that contained very small particles, and we were supposed to measure their conductivity. And we have used the SEM to precisely navigate the AFM tip to the particle. And as you can see, some of the particles were non-conductive. That's represented by the black curve. Some of them were more conductive. That would be the blue curve. And the most conductive particles are represented by the red curve. So let's move on to the mechanical properties. And here we will establish the local mechanical properties by energy dissipation on sample that contains polyethylene islands embedded in polystyrene matrix. So the lower part of the image represents topography of the sample, and the upper part represents the energy dissipation, showing the polyethylene image represented by yellow color. That means that they are softer. And then the polystyrene represented by the blue color, which means that the polystyrene is harder. And if it's going to work for your application, you can correlate the topography with energy dissipation for better data interpretation. And also you can roughly quantify the local sample hardness by doing force distance curves. And as you can see here, there are two different curves recorded for the polyethylene and for the polystyrene. And as you can see, the slope of the curve for polystyrene and polyethylene is very different. And from the slope, you can calculate the local sample hardness. In this last application example, the LiteScope is shown as a standalone AFM in connection with the protective case, the Nanocase, and a camera for better orientation on your sample. Nanocase provides LiteScope with passive vibration protection and will allow you to run the measurements in controlled atmosphere. In this setting, you can still use LiteScope with most of its measurement modes, however, without the benefits that come with the AFM and SEM connection. For instance, for calibration purposes, or whenever your application allows that, the LiteScope will work very well as a standalone microscope, as shown on the included examples. So to summarize, The LiteScope main benefit is the CPAM technology, which is unique to LiteScope, and it enables you to simultaneously acquire and correlate AFM and SEM data. LiteScope supports a wide range of measurement modes. You can extend its functionality because it's customizable. You can get optional accessories, and it supports commercially available probes. If you want to, you can use LiteScope as a standalone AFM, and by integrating AFM and SEM, you will strongly enhance capabilities of both techniques. It's simply better than using separate AFM and separate SEM. You can take advantage of the accurate AFM tip navigation to the region of interest by SEM that will make your measurement extremely time efficient, and the whole time you work in in-situ conditions, which is crucial for sensitive samples. And importantly, it opens up the possibilities of sample analysis that were simply not possible by separate AFM and SEM systems. So with that, I would like to thank you for your attention, and I hope that all the benefits of combining AFM and SEM instruments and all the new possibilities in data correlation were explained clearly. And please stay with us. Video of LiteScope integration into SEM and sample measurement demonstration will follow.
Okay, before we go into session of Veronica Hargrove, just a reminder, I see that a couple of questions are coming, but for those of you who didn't have found the place, if you wanted to ask question, look for live event questions and answer. You have that control with question mark name show Q&A at the right side of meeting control bar. Joseph or Veronica will try to answer all your questions. And indeed, at the end of the today webinar, there will be session where Veronica and Joseph will answer verbally the most frequent questions, or they will find something interesting to add to the questions, so we will give them floor. Now Veronica Hargrove is ready to show and tell you about sample, then how to install and operate the LiteScope inside SEM, and how to get results and process them. So enjoy, please.
Hello, I'm Veronica Hargrove, Application Specialist of NenoVision Company. I would like to talk about an easy integration of AFM microscope, LiteScope, into different secondary electron microscopes and their simultaneous acquisition, correlative probe and electron microscopy. We are going to measure two kinds of steel alloy. The first sample is strip steel, which is chemically polished. The aim of etching here is to fabricate very fine and smooth surface. AFM alone gives us information about the morphology and about the roughness of the surface, but we are not able to determine the reason of diverse etching rate or of the selective etching. Because the steel alloy is composed of several phases visible in SEM, the correlation of AFM and SEM could provide us complex information about the sample surface. If we are able to determine which phase is etched faster and which one is etched slower, we can optimize the etching parameters to obtain as smooth surface as possible. The second sample is high-speed steel alloy. The contrast here is often misleading in SEM. Many times, the different SEM contrast comes from both material contrast and from topography. The question here is, are we able to correlate both techniques the way that we can precisely distinguish the individual features on the sample surface? Before we start measuring the samples, let's have a look how to integrate AFM microscope into SEM. I am going to start with an integration into one of the Thermo Fisher scanning electron microscopes, SIOS. To maintain the chronology, I start with procedure of exchanging flange with feed-through and cable connection from the feed-through to the controller, Nanobox. These steps has to be done only for the first time, because the outer connection does not interfere with SEM when LiteScope is not in use, and so we don't need to remove this. We are going to continue with installation, which has to be done by each user. The only thing which has to be removed is SEM sample holder. First, we fix an adapter to the stage, which is rotated in a proper position, and we fix the LiteScope with 3 screws to the adapter. Finally, we connect the LiteScope cables into the feed-throughs leading to Nanobox. Now it's time to load the sample and the probe. We fix the sample on an SEM stub by 1 little screw, exactly the same way as to the usual SEM sample holder. The probe, your commercial Akiyama probe, is placed into a probe holder, and using tweezers, we load the probe into the holder in the LiteScope. As you can see, there is enough space between the sample and the probe, so these steps can actually be mixed up. Finally, we roughly move the probe tip to the area of interest by eye, and even finer in that direction. I will talk about the probe movement later as we start working in the NanoView software. Now we can close the door and double check the cables. Now we are going to have a look how to measure AFM and SEM together. During the pumping, we move the LiteScope under an SEM cathode. As I skipped SEM adjusting, because it works the same way as SEM alone, I can also safely come closer to the cathode in a Z direction. We find an interesting spot on the sample for us and improve focus. The SEM is all set, so we log in NenoView software and log the microscope, so no one except us can change the AFM parameters now. We create a new project and save the destination of later observed data. As we did not move with SEM stage, we are still in the area of interest. We are just zoomed out. We roughly move the tip closer to the center. We can zoom in and check again the position of interest and continue in the movement of the tip. How do we do it? We use Macromotors box in NenoView. I cut a window here. As we are zooming in, for now we are using X and Y direction. We can also change the step in Macromotors to move finer with the tip. When we zoom in, let's say we are close enough in X and Y direction. But before approaching, we are going to adjust the AFM parameters. First, we sweep the Akiyama probe to find its resonant frequency. We are looking for an axial symmetry of the amplitude graph, because each tuning fork of the probe is different. We compensate it by tuning for compensation in the probe offset window and zoom in to sweep the frequency with higher resolution. Further, we lower the sine amplitude quite a lot here because the amplitude should be around 0.5 for the first approach. As we select the working frequency, which the probe will maintain on during the measurement, we approach the surface automatically. Let's watch the upper right corner. The moving red scale and the z-axis graph below schematically show the piezo expansion and contraction. The piezo under the scanner is moving towards the tip as the probe does not feel the set frequency shift. The piezo is contracted and the probe jumps 50 micrometers down. The process is repeated till the tip is in contact with the sample. As we arrive to the surface, see the left BSE image from the top. Let's have a look in the tilt. When we zoom in, the very tip is really in tapping contact with the surface. We could have measured in the tilted position. It is useful especially for FIB applications, but I am going to move back to 0 degrees. Last thing to do is to set the electron beam point close enough to the tip in SEM and set the image parameters in NanoView. We will measure the range of 20 micrometers squared with 512 points and start the measurement. First, we need to adjust the parameters. We will measure a few lines and correct especially the slope. You can see it in the graph that the slope is changing. And we need to lower the integral parameter because there is a lot of noise in the graph. Also, we higher the set point. You can see it in the left in the feedback AFM box. And we push a little bit more to the surface. Now we check the SEM channels, secondary electrons and backscattered electrons, if the sample is properly focused before we start the measuring again. Now we would start with scanning the sample. Usually it takes approximately 10 to 20 minutes to obtain the CPAM image. You can see in the tilted SEM view how the sample is scanning and the probe is staying still on one place. I speeded up the observation. You can see that we collect at the same time from the same place AFM topography, secondary electrons, signal, and backscattered electrons. After the image is measured, we retract the probe by retract button and save raw data. To eliminate the offset, we use the CPAM button. Choose the channels of each method we would like to correlate and match the same spots. You can see in the image below that we have SEM image a little bit transparent, so we can see both signals together. From the matched points, automatically we have corrected offset. Using pulse opacity or changing the transparency by hand, we can also improve the correction manually. Finally, we choose all channels to be correlated together and save the data. Let's have a look at the processed and saved images of the trip steel. It's nicely visible how important the simultaneous measurement is. We are able to distinguish different phases and its boundaries thanks to SEM signals, but we need AFM to determine which phase is etched more and which less. It enables us to optimize the etching process to obtain the smoothest surface possible. Now, I would like to quickly repeat the integration and measuring procedure on a different brand microscope. We use Tescan Lyra 3, provided by Central European Institute of Technology in Brno. As you can see, we exchanged the SEM sample holder for a LiteScope, plugged in the cables into the feed-throughs, loaded the sample and the probe, and finally checked the cables that do not interfere with anything in the chamber. The easiest way is to move the stage under the cathode while the SEM doors are still open. When everything is integrated, we just close the door and pump the chamber. I've already adjusted the SEM, so we can move with the stage, in this case LiteScope, closer to the cathode. We only need to improve the contrast, and then we are able to find an interesting area on the sample. While we zoom out, we'll leave the stage stationary. We zoom out till we see an AFM probe somewhere in the corner. Now we move the AFM tip to the area of interest. Because we didn't move with the stage, we just go approximately to the center with AFM tip. According to macromotor's step, we move in X and Y direction. And we zoom in and go closer and closer to the area of interest. Thanks to SEM, we can change the focus between the sample surface and AFM tip. It enables us to safely approach the tip much closer to the surface manually, and so it shortens the time necessary to approach automatically. When we get closer, but still we are not in contact, we sweep the probe to obtain the resonant frequency. I skipped this part because we have already done it before, and so we approach the surface automatically. You can see that sample surface is changing. It means that the piezo is going down, contracting and expanding. Because the scanner was moving in the Z direction, we improved the focus and then placed the electron beam point close enough to the tip. We start the 20 micrometer squared scan and adjust the image parameters in NanoView. We can change the view to see more images at the same time. The sample would be scanned for 14 minutes now. I speeded up the imaging to see that we are really simultaneously obtaining several AFM and SEM channels together. We can, of course, choose which one of them we would like to see, and so at the same time of the measurements, we can compare the information. After the measurement, I tilted the stage for better visibility. and we retract the tip with a retract button. In this case, the macromotor moves with 50 micrometer step away from the sample surface. As we zoom out and we are pretty far away from the sample surface, I tilt the stage back to 0 degrees. You can watch the tilting of LiteScope in the right part of the slide. The next procedure may be done before, during, or after venting the chamber. Pressing the buttons in the macromotor's box and choosing the step, we move the tip away from the sample. It is especially useful when changing the sample with no need of exchanging probe. The measurement is all done, so we remove the LiteScope the same way as we installed it before. We only need to remove the offset caused by placing the electron beam spot next to AFM tip. We choose few same spots in AFM and in SE image. Then we have a look at the bottom image and manually improve the automatic correction. On the right side, we choose the channels to be saved with the offset, and in the right column, we press Save. Now the file contains both raw data and the correlated set of images. In the left channel is correlated topography, in the right one is BSE signal. The bottom image, as you see, shows exact 2D CPAM image. We are moving to the last part of this presentation, and the question here is, how do we post-process the observed data? The data measured in NanoView are compatible with Gwydion software. We open the correlated channels from Data Browser and post-process each one of them alone. These images that you can see are from the exactly same spot measured simultaneously. We can change the color of each one of them, the tilt, contrast, etc. to show the most on the image. We can save either 2D images, each one of them alone, or we can open the topography in 3D. Like this, we can have a look at the sample morphology from all sides and to decide which one of them is the best. Further, we overlay the correlated SEM signal, either SE or BSE. In Gwydion, you can change the color of the overlay, you can change the light, angle of the light to see the most of it, and you can also change the height ratio. Like this, we can process the 3D images and save in all signal combinations. The CPAM imaging of high-speed steel allowed us to distinguish different features on the surface. From the correlation, we can see which phase is higher, which one is lower. It is probably due to the fabrication process, but we can also see the diversity within one grain. Because on the BSE image, CPAM BSE, you can see that it is one grain on the left, but you have two colors of BSE. So it means you have within one grain two phases. I would like to quickly summarize this section that we've seen now. I showed you, independent on the SEM brand, that we are able to easily integrate the AFM LiteScope into SEM within 5 minutes. The operation and measuring procedure is intuitive and really saves a lot of time. During both measurements, I have shown you few of the advantages of AFM in SEM, but I would like to exaggerate two of them. It is really easy to localize the area of interest by SEM and then navigate the AFM tip exactly to the chosen area. And second of all, The CBAM imaging, which simultaneously acquires several AFM and SEM signals, really helps us to obtain complex information about the sample surface, the topography, and the material characterization. That's all from my side. I would like to thank you for your attention.
Dear all, thank you for your attention. So now we are starting the Q&A section. So we have tried to answer as many questions as possible in the chat window. However, we've chosen a couple of important ones that we feel is better to clarify this way. So the question number one is, if the recording is going to be available, and of course, yes, the whole recording of the webinar is going to be available. Then we have a couple of technical questions. So another question is, you have mentioned self-sensing probes. What does it mean? And what is the difference compared to standard AFM probes? So these standard AFM probes used for detection of cantilever displacement optical detection system with lasers. And the self-sensing probes do not use an external optical detection system, and the sensor is an integral part of the probe. So the difference is mainly in the sensing mechanism, and the sensing and the actuation of the self-sensing probe will strongly depend on the particular type of the probe. So we have mentioned tuning forks, we have also mentioned silicon cantilevers. But as we have said, we can operate almost any type of the probe. So the next question is, what is the maximal size of the sample which you can measure? So the sample scan size, it's 22 by 11 millimeters, but of course the sample itself can be bigger. It is important to mention that the maximum sample height is approximately 10 millimeters, and that will depend also on the probe holder that you will use, and also the coarse approach option that you will choose for the LiteScope. And if you would like to accommodate taller samples, on request, this can be done with a customized coarse approach. Then we have interesting question. What is the minimal working distance which you can get? So 4 millimeters is usually the minimum working distance. But bigger working distance might be needed for different probe geometry. Or for instance, when you use a LiteScope in tilted position, for instance, for FIB applications and so on. So the lowest working distance that we have achieved was 3.2 millimeters. Another nice question. Can I use LiteScope on more than one SEM? What do I need for that? So of course, you can use LiteScope on a couple of several SEMs. It's very easy. The only thing that you need is the appropriate flange for the SEM. And then you can just move the LiteScope and the control unit from one SEM to another. So there are no limitations. And there was one question answered in the chat window, I believe, but I think it's important to mention it again. So if I want to measure electrical or mechanical properties, do I need to change some modules, or how is it done? So what is always needed is an appropriate AFM probe. So each technique might require different probe and probe holder, and the operation is absolutely routine, and you don't need anything special. So, but for some specific advanced electrical measurement like KPFM, PFM, and some others, you might need additional lock-in amplifiers, and this item is an optional module which you can, of course, purchase. Okay, so with that, I would like to close this section. So if you will have more questions, please visit our webpage, which is nenovision.com, or you can also contact us directly via email. And I would also like to invite you to the rest of our webinar series that are called Coffee Breaks with NenoVision, that will explain more into details the most important aspects and applications of LiteScope and the AFM and SEM concept. So the next one will be focused on correlative microscopy using CPAM and is streaming next week on June 25th, and then the others will always follow 1 week apart. So with that, we are coming to the end. And on behalf of the whole company, I would like to thank you for your attention. Well, and see you at next webinar.